In this lecture, we're going to continue learning about spinors, and we're going to specifically talk about going between the spinor and the magnetization domain so that we can start to form desired excitation profiles that relate to specific rotations that we want to generate in MRI. And then we'll go over a survey of sort of other spinor calculations. Okay, so recall from the previous lecture, lecture 25, that the spinor phi, which is defined as the vector alpha and beta, where these are the two Cayley-Klein parameters, and they're complex valued, this spinor completely determines a rotation, and it's everything that you need to know about. And if you calculate these two parameters for an RF pulse, it's everything you need to know to calculate its rotation at a given location. The spinor depends on half angles. That is, a rotation by 2 pi is not the same thing as a rotation by 4 pi. And this simplifies pulse design for angles that we care about in MRI, which are between 0 and pi radians. So, and we can convert from the magnetization domain, that is the three Cartesian coordinates, to the spin domain by calculating the rotation rate, omega, or the rotation angle, omega, which is minus gamma times the length of the components of the RF magnetic field in the Cartesian domain, and the rotation axis n is equal to gamma over magnitude of omega, so it's normalized here, times the three components of the magnetic field. So we divide by omega to normalize it so that n has length 1. And so these two parameters, and then theta is equal to omega, calculated as here, times the length of the RF pulse, delta t, the subpulse, for like one time point. So these two parameters, n and theta, are in the magnetization domain, and they determine alpha and beta in the spin domain, as before, which we talked about in lecture 25. We can also go backwards from the spin domain to the magnetization domain. So for a given phi, alpha and beta, the observable magnetization components can be calculated as mx is equal to phi complex conjugate times sigma x times phi. My is the same thing but with sigma y, and mz is the same thing but with sigma z, where these matrices, these 2x2 spin matrices, sigma x, sigma y, and sigma z, have the same 2x2 definitions as before. And the phi at the end of the pulse is equal to the overall rotation matrix of the pulse times phi 0, the initial rotation, where if you recall, phi 0 was this phi 0 is going to be some alpha 0 beta 0 multiplied by the 2x2 matrix generated from the Cayley-Klein parameters of the RF pulse, alpha and beta. So then Q here is the rotation matrix that's induced by the pulse. And in the previous lecture, we said that if the magnetization is initially along the plus z axis and theta 0 equals 0, then phi naught here is cos 0 minus I nz times sine 0 minus I nx plus I ny times sine 0. The only term that doesn't go away here then is the cos 0 term, which is equal to 1. So that's equal to 1, 0. So then phi is equal to the rotation parameter matrix of the pulse, the Q matrix, beta alpha complex conjugate, times 1, 0. So we're just sifting out the left column of this, and we get alpha beta. And we said earlier that phi was the spinor corresponding to the pulse. Okay, and we can then compute mx, my, and mz from this by plugging it in with the definitions on the previous slide. So we get phi transpose, or phi complex conjugate transpose, is alpha conjugate beta conjugate. Then we have sigma x. Then we have alpha beta, which is equal to alpha complex conjugate beta plus beta complex conjugate alpha, equals 2 times the real component of alpha complex conjugate beta. Then my is similarly alpha conjugate beta conjugate 0 minus I 0 alpha beta is equal to minus I times alpha conjugate beta plus I times alpha beta conjugate which is equal to 2 times the imaginary part of the same term here, alpha conjugate beta. mz is different, though, since it has entries on the diagonal of its rotation matrix. Alpha conjugate beta conjugate 1 0 0 minus 1 sigma, that's sigma z, is alpha beta, which has a simpler expression, alpha alpha conjugate minus beta beta conjugate. Recall then again that earlier we said that in order to still only have 3 free rotation variables, we have to enforce that alpha conjugate plus beta beta conjugate equals 1. That is the norm. That's equivalent to saying that the norm of the spinor has to be 1, or that we have an orthonormal rotation matrices. And if we apply that to combine that with this equation, we can derive that mz more simply is equal to 1 minus beta beta conjugate minus beta beta conjugate, right? By solving this equation for alpha conjugate and then substituting it there. And that's equal to 1 minus 2 times beta beta conjugate. So it's a simpler expression that then only involves beta. As usual, we'll be interested in the mxy components here. That is the complex valued transverse magnetization that our pulse produces when we're thinking about excitation pulses. That's what we'll be interested in. And so we need to combine the mx and my equations to get alpha conjugate beta plus beta conjugate alpha plus I times minus I alpha conjugate beta plus I alpha beta conjugate. And we can simplify this down. So we get alpha conjugate beta plus beta conjugate alpha plus alpha conjugate beta minus alpha beta conjugate. And so you can see that we lose this term and this term, which cancel, and the other two add together to give us 2 alpha conjugate beta. So a simple expression then involving the rotation parameters of the pulse for the magnetization mxy complex value magnetization mxy that it produces. We can compute the various terms for mxy and mxy conjugate and mz and collect them into a whole big 3x3 rotation matrix, which relates these terms to the terms after the pulse to the terms before the pulse. So this m vector here is m after the RF has been applied, and the m here on the right, which we denote with the minus sign, is the m before the RF pulse is applied. So we have some important special cases here that we're going to use in SLR pulse design. The first is the excitation profile, which we showed earlier, is equal to 2 times alpha conjugate beta conjugate. You also have to consider the initial longitudinal magnetization here, but really, if you're designing a pulse, you don't really think about that. But technically, m naught is there. The mz after the RF pulse, assuming that you have also all the magnetization relaxed along mz, along the z-axis, then for mz after the pulse you get alpha alpha complex conjugate minus beta beta conjugate times m naught, which we showed earlier is the same thing as 1 minus 2 beta beta conjugate. And then in the spin echo profile case, we have a different initial magnetization where we have mxy conjugate, that is, all the magnetization is in the transverse plane. So that means that after the refocusing pulse, we will get alpha complex conjugate squared times mxy before the pulse minus beta squared times mxy before the pulse complex conjugated. Okay, and we'll be visiting these relationships more as we go into SLR pulse design. Now, thinking about the spin echo case more closely, we only want the mxy minus complex conjugate term to appear in the overall spin echo profile expression, so that phase that's accrued due to off resonance in the first TE/2 period is canceled in the second TE/2 period. That is, if we do a proper pancake flip with our 180-degree refocusing pulse, then we will have complex conjugated the transverse magnetization from the first TE over 2 period, such that all the phase that's accrued due to off resonance in that period is canceled with the phase that's accrued due to off resonance going in which will go in the same direction in the second TE over 2 period. So to illustrate why this is graphically, consider this spin echo pulse sequence. We have a 90-degree excitation here, then we have half the echo time period before we play out the 180-degree refocusing pulse, then we have the other half of the echo time period until we expect to see a spin echo signal. So specifically, let's consider two isochromats or spins, which have experienced opposite off resonance frequencies. We're going to mark them with an X and a circle. So at time one here, right after we've excited them, they're going to be in the transverse plane, right? This is the XY plane. They're both going to be in phase because they haven't had any time to accrue their different off resonance induced phase. When we get to time 2, right before the 180, they will have experienced some phase due to their off resonance. So the circle here we're indicating would experience theta 1, this phase theta 1 due to off resonance, and the X vector here, isochromat, would experience this off resonance induced phase theta 2. The 180-degree pulse is going to pancake flip these. It's played out on the x-axis, so this is the rotation axis here, so it flips the circle over down here and it flips the X up here, right? And then you're left with this configuration. Now the X vector has minus theta 2 phase and the circle vector has minus theta 1 phase. So now the phases are complex conjugated. And because we've complex conjugated them, now the X here is going to accrue another theta 2 phase, right? Which is going to go this direction. So it's going to cancel out and it's going to move down here, down back to the x-axis. And likewise, the circle vector here is going to experience theta 1 phase going this direction, so it's going to move back up to the x-axis as well, so that they'll be in phase at time 4 when we care about sampling the signal getting high signal back. So we only want out of the spin echo expression, we only want the minus beta squared times mxy term in mxy plus equals alpha squared times mxy minus beta squared times mxy minus. We only want this term to be left over. And it looks like I've left off minus complex conjugate here. That is, we don't want the uncomplex conjugated magnetization. That represents a failure of the spin echo refocusing pulse if we have any significant term here. So in fact, since theta equals pi nominally for a refocusing pulse, and NZ is 0, then nominally the alpha rotation parameter is 0 anyways, right? Because if we plug in pi here, then we get cos of pi over 2, which is 0, and NZ is 0 because there should be no overall Z component to the refocusing axis for the overall pulse, and so we should get 0 anyways. And in that case, the undesired alpha squared mxy minus term won't even show up. But in the slice selective pulse, theta cannot be pi everywhere, or not really anywhere actually. And specifically, the flip angle won't be equal to pi in sort of the troughs of the passband ripples, and it won't be pi in the transition bands, and it won't be pi in the stop bands either. And so this is why we use what are called crusher gradients on either side of the 180-degree pulse to kill off the alpha squared mxy minus term. So let's see what happens when we do that. So the phase that's accrued due to one crusher gradient is equal to the integral over that gradient over time times minus gamma times the x position, the spatial position x. And then we can build that into a spinor rotation matrix, a spin domain rotation matrix, and obtain this crusher rotation matrix Q, which has only terms on the diagonal because only alpha is non-zero if NZ is 1. Right? So if NZ is 1, as it is for a gradient pulse, then beta will be 0 because NX and NY will be 0. And so then you'll only have an alpha rotation, and it'll be a pure complex exponential. Then we can sandwich the 180-degree refocusing pulse between two identical crushers in time, right? Here I'm illustrating two identical crushers, and in the middle is a 180 pulse. So you see this, the magnetization sees this crusher, then it sees the 180, then it sees the second crusher. So then we have the rotation matrix due to the crusher, the rotation matrix due to the RF, the rotation matrix due to the first crusher, and the rotation matrix due to the second crusher. And if we multiply all these together, then we get these terms, right? So the crushers, it turns out, the crusher terms cancel out on the beta parts on the betas of the overall Q matrix, but they are maintained on the alphas. And you can probably appreciate now that we're going to be left over with these big phase shifts on the alpha terms of the overall spin echo signal profile. So then overall, the magnetization profile with crushers turned on is given by mxy plus is e to the I2 phi of x, that's the 2 times the phase induced by each crusher, times mxy minus times alpha squared complex conjugate minus beta squared times mxy minus complex conjugate. So, and what we call this is the crushed term. And this guy is the refocused term. So you can see that the refocused term was left alone. With or without crushers, it's the same. When we add crushers, we only add this phase shift onto the crushed term. And we assume that the crushers are big enough that we get enough phase over one voxel that the signal from that voxel and of the crushed magnetization will cancel out to zero, will integrate to zero over space. So this signal can still be laying around, but we're assuming that it has enough phase due to the crushers that it's going to be dephased and you're not going to get any signal from it. So for the purpose of designing spin echo pulses, we are going to assume that we have crushers and focus on only designing this minus beta squared mxy minus term, that is, which corresponds to the refocused or spin echo signal. The other reason we use crushers is to kill transverse magnetization that is generated by the 180 from the MZ left over by the excitation. That is, because our refocusing pulses can't possibly be perfect, we will get some MXY generated from the 180, and so we play out another big crusher gradient after that 180 to kill off that signal. Okay, so in the next lecture we're going to talk about the Shannara-LaRue transform, because now we've got all the background math that we need to do that.